Again, this is CS 746, Perspectives on Data Science. It is Wednesday, February 5th. Today's topic is going to be statistics for data science. If people are listening to this recording and it is bad quality, please let me know. We have technical issues. The podium computer is not logging in today, so I'm using my laptop and using the speaker on the laptop. If it's bad quality, I need to know. So, okay, so again, we're down here. We have if we were following the outline strictly, we'd be jumping onto data visualization, but we want to get through the statistics first so we can understand what the visualizations mean. So we're going to kind of do things in, the order of what makes sense rather than the order of the basic visualization. So statistics for data science include descriptive statistics. How do we describe what the data looks like, right? Probability theory, inferential statistics, linear regression, correlation, multivariate statistics. We're going to do statistical modeling and machine learning. We have to worry about time series analysis, and we have to worry about Bayesian statistics. And there's a whole story behind Bayesian statistics. Apparently, there were like statistics wars back in up through the 1990s, and statisticians were arguing about the right way to do statistics. And eventually they realized that they were arguing over semantics, and it was a silly fight, but there was this real actual thing where statisticians were like mortal enemies, as it were, with each other because one was a Bayesian and the other was a frequentist. And hilarious stuff. The smaller the thing, the more excited people get about it. So we're going to cover these things in this class, and we're going to get started off today and kind of do a sort of overview of things and then get a little bit of detail. So our descriptive statistics are, what does the data look like? So we want to see what are our measures of central tendency. The mean, the median, and the mode are the three measures of central tendency. We want to look at how dispersed the data is. What's the range? What's the variance and standard deviation, very closely related terms, and the interquartile range. We'll look at data distributions, the skewness of a distribution, the kurtosis of the distribution. We'll look at tools that kind of like give us summaries of the data. These are kind of visualization by text or by, in the case of a box plot, actual graphical visualizations. So, we get around to the visualizations eventually. Probability theory. Our basic concepts are the probability rules, addition, multiplication of probability. Conditional probability, if event A occurs, what is the likelihood of now seeing event B, right? And the Bayes theorem, of course, is an application of conditional probability. Random variables, the two types, discrete versus continuous. Are you a gambler rolling dice? That was how statistics started. People wanted to be able to make money at the casinos back 200 years ago, 300 years ago. And so they were figuring out what the probabilities were that the dice were going to come up the right way, right? Or continuous, what is the temperature, right? Probability distribution functions. There is the PDF and the CDF. The probability distribution function is what is the likelihood that we'll get a certain value. Cumulative is what is the likelihood that we'll get less than or equal to that value. So, of course, the small numbers, it starts at 0. And then by the time you get to the larger numbers, the end of the probability distribution is close to 1, right? We'll talk about some common probability distributions: binomial, Poisson, normal, uniform, exponential. We're going to talk about inferential statistics, aka hypothesis testing, the null, the alternate hypothesis, p-values, significance levels, also called alpha. We'll talk about type 1 and type 2 errors. We'll go into some statistical tests, the z-test or z-test if you prefer, and the t-test or student's t-test. And on those tests, we have one sample, two sample, and paired. We're going to we'll briefly touch on chi-squared. We're not going to go into huge detail on that. That's used for population biology largely. And we're going to talk about analysis of variance, or ANOVA. We'll look at confidence intervals. You do a statistical analysis, it will never give you an answer yes or no. The statistical analysis will always give you a confidence interval. I am 90% sure that my answer is right. I'm 95% sure, right? We need to know what that means. Regression, we're going to look at simple linear regression, multiple linear regression, logistic regression. We'll discuss polynomial regression briefly. We'll do ridge and lasso regression. We're going to look at some of the correlation analyses, Pearson, Spearman, and covariance. We'll discuss goodness of fit measures, R-squared and adjusted R-squared. And every one of these, some of these will go into much more detail than others. So multivariate statistics. How do we deal with multiple variables that are closely related to each other? One of those is called principal component analysis, where we take highly correlated variables and remap them into a different dimensional space so that we have something else that's not correlated with it, the things, weird stuff there. So matrix theory, math is wonderful. Singular value decomposition also. We'll also look at how to do clustering and grouping, k-means clustering, hierarchical clustering, DB scan, multivariate linear regression, exploratory factor and confirmatory factor analysis. We'll look at statistical modeling, machine learning. So we're going to discuss the confusion matrix, the precision recall and F1 scores, how to tell how good your model is, right? ROC and AUC stands for receiver operating characteristic and the area under the curve. We're trying to differentiate between two things. We're measuring a receiver operating characteristic curve. It tells how well a signal is received. That actually comes from radio history. And we're seeing how good our model is by how much of the data is under our curve and how much did we miss, right? We're going to do cross-validation. You know, we want to come back and make sure that the answers we got are right. Bias variance trade-off. You can have higher bias, but or you can lower the bias in your model, but that will give you higher variance. You can lower the variance, but that will tend to give you higher bias. So that's just a trade-off that exists. We'll talk about resampling techniques, bootstrapping, jackknife. We'll do time series analysis, key components, trends, seasonality and noise, and stationarity. So do we have something that changes over time? Do we have something that we can assume is kind of a stationary, it's all the same regardless, right? So we're going to look at autoregressive models, moving average models, autoregressive integrated moving average, and seasonal autoregressive integrated moving average, ARMA and SARMA models. And these are ways to deal with, you know, if you're running a store and you're selling Christmas items, your sales are always going to go up around Christmas, right? So, you know, you don't want to take a trend and say, oh, look at things are going great because I'm doing so much better in November than I did back in January or in July, right? So you have to deal with that seasonal variance. And there are ways to do that by smoothing it. And finally, Bayesian statistics. We're going to do Bayesian interference, the prior probability, the likelihood, and posterior probability. We're going to do Markov chain models and Monte Carlo methods. Experimental design. Randomized controlled trials and A/B testing are major ways that we do experiments. Sampling methods. We do simple random sampling, stratified cluster sampling. How do we determine the right sample size? In A/B testing, one of the key features is to make sure you don't make either a type 1 or a type 2 error, right? So you want to be able to understand what the likelihood of making of the two main kinds of errors in statistical analysis. So blah, 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 zoomed right through that, right? Now we're going to go into some of the more details of it. So we're going to start with our descriptive statistics. Again, we are looking at the data to try to understand what it looks like. So these will tell us what the characteristics of a data set are. They won't help us make any inferences or predictions. They'll just give us a feel for what our data looks like. This only makes sense with numerical data. If you try to do this for categorical values, you know, it doesn't work as well at all, right? So if you try to go out there, do an analysis of, we'll see average, football team, right? Well, what's the best football team? Well, people up in Kansas City will clearly tell you it's clearly Kansas City. People in In Spain, we'll tell you it's clearly Real Madrid, different type of football, right? So the mean, of course, is our primary measure of central tendency. And not all numbers does the mean make sense with, but we're going to just take all the observations we have, sum them together, divide by the number. So 2, 4, 6, 8, 10, we add those together, we get 30. We divide that by the number of observations, 5, and the average of those numbers turns out to be 6. Okay, so for the data set 2, 10, 33, 34, 35, 54, 65, what is the mean? I will see if anybody can figure this out. Calculator? I don't think we put the thing up here. So we were supposed to have the answer on here. And I think Harika calculated that and forgot to tell me what it was. So basically, we just add those numbers together, divide by 1, 2, 3, 4, 5, 6, 7, and that is the mean that we would get. Anybody got an answer yet? 33? What? 32.8? Okay. What? 0.28. 32.28, yes. All right. And that sounds reasonable. Okay, so, and did we do it right? Who knows? So how do you calculate the mean for large data? Well, the more stuff you do on there, the longer it takes to type it into your calculator. So for large data, you use a computer, right? Is the answer, right? And that's why we have Python and pandas. So descriptive statistics, the next one is the median. If we sort our data from the least to the most, the one in the middle is the median, right? And then from that, we can make observations about the skewness of the data. For instance, if we look at house prices in the United States, the average house price is much higher than the median house price. Why? Because the data is skewed by a smaller number of very expensive houses, right? And a large number of more moderately, well, historically, large number of moderately priced houses. That's getting out of hand right now, right? So in this case, 2, 4, 6, 8, 10, we've got 5 values. We pick the one right in the middle, right? And we get 6. If our data set had 4 observations, an even number, then we take the 2 in the middle and we average them. So we'd average 4 and 6, we get 5. Okay. The mode is the most frequently occurring value in the data set. So there can be one mode, there can be 2, 4 modes, there can be multiple spikes in the data where there's a value that's most common. So if we had, 2, 4, 4, 6, and 8, the mode is clearly 4. If we had 2, 4, 5, 6, 8, there would not be a mode. There is no most common number. They're all the same. If we have, or the mode would be everything, right? Uniformish. If we have the data set 1, 1, 2, 2, 3, we're saying, well, this is kind of bimodal. There's a 1 and a 2, right? The fact they're right next to each other says that if we drew a bar chart, we wouldn't tell the difference. Right? So now we're going to look at measures of dispersion. So we want to see how variable our data is. Did we collect all the data and we came up with the same number for everything? We measure the height of everybody in this classroom. Do we get the same number for everyone? Or is there going to be some outliers, Are there going to be shorter and taller? Obviously, we expect to see some sort of a normal distribution, right? So we're going to look at the spread. So the first one we could do is just a range. What's the smallest number? What's the biggest number? The difference between the smallest and the biggest observations. Just subtract the min from the max. And then we can look at the variance. This is probably the most important one. There's a population variance for the overall population. Imagine all the students at Wichita State University is our population. Our sample is the students that are in this classroom. So we're just going to measure those. And again, in this case, sigma squared for the population is the term what we use, and S squared is what we use for the sample, just to indicate that there's a difference, right? So mu is the population average. Over here, X bar is our terminology we use for the sample average. We take each individual value in our population or sample. We subtract the mean from that, right? And so now we have a whole bunch of distances. We square those distances. We divide by the total number in the population, and that gives us our population variance. Over here, we use n-1 for the sample. Because when you have a sample, the likelihood that your data is a little broader is actually a little higher. So we do an adjustment on there to make it closer to what we think is the real population. That's oversimplified. Example, data set 2468. The mean is therefore 5. If we add those all up and divide by 4, we get 5. So we have to subtract everything from 5. We get 3 plus 1 plus 1 plus 3. We square all those, so it's 9, 1, 1, and 9, which gives us 20. Divided by 4 is 5. The standard deviation is nothing but the square root. Do you have a question? Okay. If any has a question, just throw something at me or raise your hand. The standard deviation is nothing but the square root. And I'm sure many of you have already studied this and you're sitting here going, why do we have to go through this again? It's the same reason we had to go through Python again, right? So this basically represents approximately the average amount by which values deviate from the mean. And why do we use a squared for the variance? Because farther away values, we want to have it weight more in our calculation. That's why the variance uses squared values on there to calculate that, right? If we were to just average up the deviation or the distance from the mean, we'd get a value that was not exactly the same as a standard deviation, but relatively similar. IQR, interquartile range. This is the range between the 25th percentile and the 75th percentile. 25th percentile is the spot at which you've passed 25% of your samples. Q2, where you pass 50% of your samples, that's the median, right? So you could say that 25th percentile or Q1 is the median of the bottom half of the median, and Q3 is the median of the top half of the data set, right? For 2, 4, 6, 8, and 10, Q1 is 4, Q2 or median is 6, Q3 is 8. The IQR therefore is 4, is 8 minus 4 is 4. So this is where we have a big data set, this gives us a feel for how spread out the data is, and then we can calculate the outliers beyond those IQRs and see how many far away points there are, box plots. To calculate percentiles, first we arrange the data in sorted order, just like calculating the median. We find the rank for the percentile. So if we want 30th percentile, 25th percentile, whatever, right? So the rank or position for that percentile is calculated using the percentile times 100 or divided by 100. So back to a fraction, times 1 more than we have observations on the bottom. So, and then we divide, and then that gives us the rank. So 25 percentile, n is the total number of data points. If r is an integer, the percentile value is the data point at position r. If r calculates out to be not an integer, we generally do an interpolation between the two closest data points. So if we get like a 3.33, we'll go 1/3 of the distance between the two variables. So for instance, Q1 and Q3 on this data set, it's already sorted. N is equal to 7. So we want to calculate what R25 is. Well, we want 25. We're going to divide that by 100. We're going to take 7 plus 1 is 8. So we do that calculation and we get 2. Get 1/4 of 2. The parentheses on here should be a little bit better, but this is basically saying 0.25 or 1/4 times 8. And this is 3/4 times 7. So, this is actually, according to PEMDAS, absolutely correct. This is a multiplication on the whole thing here. So if you ever see that on TikTok or Instagram, people telling you that the answer on here is that you divide by 8 at the end, they're wrong. Okay. So the second value then, 2, second value is 4, the sixth value is 12. So that's where Q1 and Q3 are in this data. Our data distribution refers to how data points are spread out across our data set. It helps us visualize the shape and variability. And the two terms we're going to look at here are skewness and kurtosis. Skewness is if we have a standard normal data set, it's symmetrical about the origin, right? So everything starts at some negative number, goes up, the highest point is at 0, drops back down as we go into higher numbers. And I didn't bring a marker, so I can't draw it on the whiteboard. There's a picture of it later. But if the thing leans one way or the other, it's bottom heavy or top heavy, that gives us a skew to it. So positive skew, right skewed, is we're higher on the right side towards larger values. We're skewed above the mean or above the median. So the mean is greater than the median. Most data points are clustered on the tail. Oh, sorry, I'm misspeak. The tail is longer on the right side. That means the data is the bulge is on the left side of the mean, right? So the skew is taller. So again, this is our housing data set. The mean housing price in the U.S. in most countries is greater than the median, right? Positive skew. Negative skew, the tail is longer on the left side towards smaller values, right? So in this case, we start measuring like heights in the class, and we get a left skewed value that tells us there aren't very many short people in the class, right? Where we delete the medium short people. Zero skew, that's what we want to see. Ideal data set. Your data is evenly distributed about the mean and the median are approximately equal. So again, you can look at kurtosis or skewness, or you can just measure the mean versus the median, see which is bigger. If they're approximately the same, that tells you how skewed it is. Examples, data set 1, 2, 3, 4, 5, 6, 7, 8, and 50. So we got this outlier out here that gives us a long tail. So our mean is going to be 10.62 and our median is going to be 5.5, average of 5 and 6. So that is positive, right skewed. There's more, outliers on the right side. Here we got 2, 3, 4, 5, 6, 7, 8, and a negative 10. Now our mean is going to be less than the median, left skewed because of our outlier on the left side. Okay. Kurtosis measures the tailedness of a data set. It looks at how heavily the data tails deviate from normal distribution. So is it a really steep value with outliers, or is it really shallow and a uniform, right? So the types of kurtosis, high kurtosis, which I will call Colorado, has heavy tails and sharp peaks, extreme outliers, right? You've got a few, so a lot of students scoring extremely high or very low. Low kurtosis, or platykurtic, or you could call it Kansas. There's light tails, there's no peak. In there's few outliers. It's basically uniformly distributed. You start rolling a single die, you'll get numbers 1 through 6. It'll be a flat distribution of the number of 1s, 2s, 3s, 4s, 5s, and 6s you roll. So we can call this Kansas. Normal kurtosis or mesokurtic, I'll call this Missouri. It's nice and hilly, right? Fun hills, not flat, not mountains you have to climb. There's no excess extreme values. It looks like a standard normal distribution in terms of the heights of the data. So kurtosis formula, where x sub I is the ith data point and is the total number of data points, right? We subtract the y values, which is the value as opposed to the number of observations. And we use, again, we see quadratic on the top and raised to the power 4 on the top, raised to the power 2 on the bottom. So here's an example. And we're not doing the calculations here, but we're just going to say we get this data set, we'll see high kurtosis because the outlier pulls out our thing. We also have a nice peak. We have 4 observations at value 5. So it looks like a steep mountain if we graph this curve. If we look at this curve, we see that they're, one value of each over a range. So that's a low kurtosis. Platykurtic, whatever. Summarization tools. 32, okay. Provide a way to describe and visualize the distribution of a data set. Percentiles, quartiles, and box plots. So percentiles divide the data into 100 equal parts. The pth percentile is the value below which p% of the data falls. Of course, the 25th percentile is the first quartile, 50th percentile is the median, the 75th percentile is the third quartile, and the 0th and 100th percentiles are respectively the minimum and maximum values in your data set. So what's the 0th percentile of this data set? 5, right? What's the 25th percentile? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values. We add 1 to it. We get 11. We take 11, we divide by 4, and we get I guess 3.25 there. Anyhow, so the value is 8.25. And the median, of course, is halfway between the two middle values, 12.5. So it's going to be 12 and a half. And the 75th percentile is going to be out here at 75% of the data. So you check my numbers on that. So our descriptive statistics and now is quartiles, and this is basically just doing percentiles in base 4, right? So you only have 4 digits to count: 25th, 50th, and 75th. You can do quintiles. You can do septiles for 7, so on and so forth. This is just a shorthand. The IQR, of course, is the spread of the middle 50%. So from our previous data, 9.75 is our IQR. Box plots visually represent the data using 5 statistics. We have a box in the middle. We can draw a box plot horizontally or vertically. Right. So in the middle, we have a line that is our median. The top of the box, or the one side of the box, is the 75th percentile. The bottom of the box, or the other side of the box, is the 25th percentile. Then off of these, you have the maximum and minimum values in the data set. If you look at the box, the IQR interquartile range is the size of the box expressed graphically. Now you go ahead and put a fence 1.5 times beyond the IQR in either direction. And the biggest value that is less than that fence is the top of the whisker, the top whisker. The smallest value that doesn't go beyond the lower fence is the bottom of the whisker. And then your outliers are all the points that are beyond the fence, right? So you think of your cows, and when they're field wandering around, and some of them have got out. They're outliers. The other cows are inside the fence. You don't draw your whisker all the way to the fence. You draw your whisker all the way to the farthest cow that's within the fence, right? That was because it's Kansas. We can do ranching metaphors, right? So here's our data set. And again, we've got median is 12.5, Q1 is 8.25, Q3 is 18, IQR is 18 minus 8.25. Our whisker limits are Q1 minus 1.5 times the IQR, which is minus 6.7375. This is our fence, our lower fence. 32.625 is our upper fence. We go back and we look at our data. The smallest number that's bigger than negative 6.25 is 5. The biggest value that is less than 32 is 21. So the top whisker goes to 21. Bottom whisker goes to 5. And we see that there's one outlier that is 30. Probability theory. The addition rule, or the union. The probability of event A or B occurring is the probability of A plus the probability of B minus the probability of A and B both occurring. Right? We draw a Venn diagram. What is the probability of drawing a heart or a king from a deck of cards? Well, there's 52 deck cards in a deck. 13 of those are hearts. So 13 over 52 is 1/4 is your probability of drawing a heart. Again, there's 13 different values of cards, 4 kings, 4 queens, so on. So 4 over 52 is 1/13 is the probability of drawing a king. Do we just add those together? No, because that would give us an incorrect value. We have to recognize that when you draw the King of Hearts, there is a 1 in 52 chance that you will draw that card that is both a heart and a king. So we subtract that back off because we've counted it twice. We've counted the King of Hearts in here. We've counted the King of Hearts and all the hearts here. So we subtract that 1/52 and we get 4/13 is their probability of drawing a heart or a king. The multiplication rule, probability of both A and B occurring, if they are independent variables, and this is an important caveat, is the probability of A times the probability of B. We have a die and we have a coin. And what's the probability of simultaneously flip the coin and roll the die? What's the probability of getting a 4 in the die and flipping a heads on the coin simultaneously? Well, it's 1/6 times 1/2 is 1/12. Okay. Probability, conditional probability of A given that B has already occurred. Expressed by PA vertical bar B. That is the probability of A intersect B given that B, the probability of B. If 30% of the students are good at math, probability of M, and 27% are good at both math and programming, probability of M intersect P, then the probability of being good at programming, given that you are good at math, is 20% divided by 30% is 67%. And if you take this and invert it, right, and say that someone is not good at math, then your probability is going to be 70% on the bottom. You get a different number, right? Bayes' theorem. We'll have more on Bayes' theorem once we figure out why the numbers didn't work out on the presentation we tried to put together. So probability of A given B, and we've already said probability of A given B is the probability of A intersect B over the probability of B, right? Well, we can also derive from that a formula. It is the probability of B given A times the probability of A, all divided by the probability of B. A medical test is 99% accurate. The disease is prevalent in 1% of the population. If a person tests positive, what is the probability they actually have the disease? Well, the prior probability of having a disease is P of A is 1%. The probability of not having a disease, therefore, is 99%. So the probability of a positive test, given that they do have the disease, again, probability of B given A, is 99%. The probability of a positive test, given they do not have the disease, is still 1%. So the probability of a positive test, and we calculate this out for the probability of a positive test using our putting things together. We add those together and we end up with probability of having the disease when you've gotten a positive test is about 50%. The test is highly accurate, but the number of people that actually have the disease is very small. So there is a more likely chance that you are in that group that doesn't have the disease and gets that 1% false rate, right? False positive, than there is that you are in the you're in the 99% of the population. Your chance of getting at 1% error exceeds the chance of getting it balances out the chance of actually having a disease and getting a positive result when you have tested the positive. Okay. Boom. Okay. 145. Discrete versus continuous random variables. Discrete variables take uncountable values. Number of heads and 10 coin flicks. Rolling a die, you can get 1, 2, 3, 4, 5, 6, right? Probability P of X equal 1. This is, I think something got messed up when we put this into this slideshow. What we're trying to say is the probability of rolling 1 in 16 rolls is 1/6 raised to the power of 16, because each time it decreases the probability for getting 2 rolls in a row. Continuous random variables, height and weight. The height of students in class follows a continuous distribution between 150 and 200 centimeters. Right. Although there are people that are taller than 200 centimeters and shorter than 150, but yeah. CDF, cumulative distribution function, represents the probability of random variables less than or equal to a value x. F of x, p of x less than x. In a dice roll, the CDF for x equals 3 is the probability x is 1 plus the probability x is 2 plus the probability x is 3. That's 1/6 plus 1/6 plus 1/6, or 3/6, or 1/2. Right? What is the probability is strictly less than 3? 1/3, right? Because 3 is not then included in that. Some common distributions. The binomial distribution, used for discrete variables with a fixed number of trials and a certain probability of success. Flipping a coin 10 times with p equals 0.5, what is the probability of getting 0 heads, 1 head, 2 heads, 3, 4, 5, 6, and so on, right? And this is not exact. This, I think, is a dice sample here because, well, no, that can't be it. Anyhow, there is always a possibility when you're flipping a coin 10 times you could get 10 heads in a row. So this graph doesn't quite match up here. Anyhow, what we end up with something that approximates a normal curve, but is very jagged because it's got discrete values in there. So the normal probability distribution function, the binomial, follow each other closely. The more different values, the more times you run your trial, the smoother and smoother your bar chart will get, and the closer it will get to an actual normal distribution, assuming you have a fair coin. Poisson distribution. This models the number of occurrences of an event in a fixed interval. So we imagine we're a call center and we're taking calls per hour, right? We usually receive 10 calls per hour on the average, then what is the probability of receiving exactly 5 calls in an hour? Well, we take our lambda argument, which is measures our spread of our Poisson distribution. We raise that to e to the minus lambda. We divide that by x factorial, and it gives us a 3% chance, 3.4% chance that we would only receive 5 calls in an hour if that's our average of 10 calls an hour. So here we can see as the lambda goes up, you know, the curve becomes more and more similar to a normal distribution. As lambda goes down, it becomes more and more similar to an exponential distribution here. Normal distribution, of course, continuous distribution. The bell curve clearly looks like a bell curve. Heights generally follow a normal distribution with a mean of 170 centimeters and standard deviation of 10 centimeters. We can use the probability of x is less than or equal to 180. We'd use the CDF of this, which would start down here, go up, hit the 50% point at the mean, and then all kind of a sigmoid curve up to 100% probability at the tallest people. Uniform distribution, equal probability over a range. You're rolling a die. What's the value probability of getting 1, 2, 3, 4, 5, or 6? It's the same for all of them. It's flat, right? Exponential, platycortosis, right? Exponential distribution models the time between events in a Poisson process. So we're standing in a street corner. Buses are traveling, you know, along, and sometimes they get delayed and sometimes they get ahead. So the time until the next bus arrives follows an exponential distribution. And the function of this is lambda lambda times e to the minus x, where lambda is our parameter that we're using for the time. Again, here we're saying like the bus comes by every 10 minutes is by the schedule, you know. This is a cumulative distribution function here. Right. Hypothesis testing is the next thing we're going to talk about. This is a method used to determine if there's enough evidence to support a specific claim. We'll do the analysis by looking at our data, determining if we first formulate a null hypothesis. Says the effect we're looking for does not exist. And then we form an alternate hypothesis, the effect we are looking for, and that is that there is an effect, there is a difference. So we say factory claims, the average weight of its product is 500 grams. Well, that sounds like there's, that if they're correct, the null hypothesis is the average weight is 500. H1 is that they're not getting the average at 500. And so that will be a two-tailed test on our Z table or our T table later. The p-value, if the null hypothesis is true, and we go out and we collect the samples, and we see an average on that sample that's significantly different from the proposed mean, then we start saying, well, that's looking more and more unlikely, right? If I start flipping a coin and someone claims this is a fair coin, and I've flipped, 6 heads out of 10 flips, I'll be okay, that looks fair. If I flip 100 times and I've got 60 out of 100, I start saying that's looking a little suspicious. The more samples I have, then the more significant a difference from our mean becomes, the lower our probability value becomes, and that becomes stronger evidence against H naught. So for instance, if we see a p-value of 0.03, which is basically we're saying we're flipping that coin 100 times, we're getting a value of 85 or 90, right? The probability of that is vanishingly small. The significance level is 0.05. We're saying, if our p-value is less than that significance level, then we reject H naught. Significance level is considered to be the threshold we decide in advance for how confident we want to be in our exam. Typically, we want a 95% confidence, so the significance level is 5%. Or we want 99% confidence, so the significance level is 1%. Right? No. Okay, it just took off on me there. Okay, so here's the p-value as expressed on a normal distribution. Again, we're counting how many times a coin flip comes up heads. And if we flip 100 times and we get 50, that's the most likely observation. But it's almost equally likely to get 51, 52, 53. We go further out, 55, 60, 65, so on and so forth. We eventually reach this point where our probability of being in that area of the distribution curve is less than our p-value that we set. So the probability of our cutoff point we set here. If we get a value farther than that, we say, well, that's unlikely, right? So testing new drugs effectiveness. We got some new drug, we think it lowers blood pressure. We want to test how effective it is. We set our H naught as no effect. There's no mean reduction in blood pressure. We run out to get 1,000 people. We give the test to them. Some of them, their blood pressure goes down, some that goes up. We want to see, is there a real effect, right? The alternate hypothesis is we want to see if it really does lower it. Does we have a reduction value that's bigger than 0? We're going to use a one sample t-test. We're going to compare the mean blood pressure reduction, taking the drug to 0. After testing 30 patients, the average blood pressure reduction is 5 millimeters of mercury with a p-value of 0.02. So if we just find our experiment, we want to be 95% confident, we'd say reject H naught. The drug is apparently effective at a 95% confidence interval. If, however, we said this is really important, this drug has serious side effects, we want to be 99% sure it actually works, or 100 or 99.999%. We can't be 100% sure it works in statistics, right? But if we set our p-value or our alpha value to 0.01, then this experiment would fail. So the difference between the alpha value and the p-value, both of those values are important. Comparing two teaching methods. Want to know if a new teaching method improves student test scores. So the H naught is the means are the same. H1 is they are different. We're not testing, is it better or worse? We're testing, are they different first? So we look at our two-tailed t-test, comparing the means of two independent groups, two samples. The mean of the first comes back 85, where standard deviation is 5 out of 50 samples. Our group B, the traditional method, we come back with a mean of 82. Standard deviation is 6 and is 50. We compare those, it would give us a p-value of 0.03 or 3%, rejecting H naught. Another example, product defect rate. A factory claims that 2% of its products are defective. Consumer group wants to test this claim. So we'll say, okay, we're going to test the claim that the defect rate is 2%. We'll assume that's okay. And our alternate hypothesis is that that claim is false. The defect rate is larger than that. We're going to do a one-tailed z-test. We're going to take 500 products. We found that 15% of them are defective. Our p-value of getting that many defective, if the actual defect rate is 2%, is 0.01, 1%. So this defect rate, we say, is significantly higher than 2%. We'll get into this in more detail in a future lecture. Company wants to know if customer satisfaction is above the neutral score. H0 is the neutral. Everybody's just kind of like blah. The mean satisfaction score H0 is that the satisfaction score is greater than 3. We're going to use a one sample t-test. Our sample mean comes back at 3.4, standard deviation of 5, n equals 100. We calculate that, plug it into our formulas, we'll get a p-value of 4%, and therefore we reject H0. But you notice that p-value is not much less than 5%, right? So, you can't really tell things from the p-value, but for sure. But when you see a p-value that's really close to your alpha value, you start wondering, should I run this experiment again, right? Gender and product preference, do women prefer this product more than men, right? So we'd use a chi-square test for independence in this case. It would say 60 males prefer product A, 40 prefer product B, females 40 prefer product A, 60 prefer product B. P-value of that happening, if they are independent of each other, is 2%. So we would then conclude with this, that gender and product preference are dependent. Type 1 and type 2 errors. Next lecture, we have a good slide on this, but type 1 error is rejecting H0 when it's actually true, right? So if you have a 95% confidence interval, what you're saying to yourself is, if I were to run this experiment 20 times, I would be willing to accept being wrong 1 out of those 20 times, right? I only want to be make sure I'm correct 19 out of 20. And you can't guarantee. Statistics is all about random chance. You could run the test twice in a row, get the wrong answer twice in a row, right? It's just vanishingly small that would happen. So false positive, rejecting H0 when it's actually true. False negative, failing to reject H0 when it's actually false, right? In that factory example, if we do our measure and we say, well, we conclude that the company's lying, they're not actually selling 500-gram products. But they really are, and we just got the wrong sample. We got a biased sample. Someone had a bad day. They dropped some of the pieces and bits of it fell off, and so the products are less than 500 grams. That would be a type 1 error. Type 2 error, they do have problems with their manufacturing, but they carefully select the samples they give to us to make sure that we get samples that look like they're doing great. And so we've concluded that they don't have a problem when they do. Medical test for disease. Again, the null hypothesis is the person does not have the disease. The alternate hypothesis is they do have the disease. If our test gives us a false positive, that will say, yes, you have the disease, when they actually don't. If it gives a false negative, it say you don't have the disease, but you actually do. The impact of a type 1 error is that they will then often have unnecessary treatment, right? Stress, potential side effects, costing them money, so on and so forth. And in general, that's why when you get a positive test on anything, the first thing the doctor does is say, let's go run another test and verify it, right? Because the chance of getting 2 false positives in a row is significantly less. There's a great joke about the statistician that read the statistic that on airplane flights, on 1 out of 100 flights, someone would sneak a gun on the board the plane. And while he knew that if you multiplied those statistics together, the probability that 2 people would sneak guns on the plane was 1 in 100 times 100, or 1 in 10,000. So he decided to lower his chance of having someone sneak a gun on the plane by sneaking one on himself. It doesn't work that way. It's a good joke. Yeah, so type 2 error, false negative. Again, in this case, we say you don't have the disease. Now they're not getting treatment. They're going home. They're saying everything's great. These weird symptoms that I'm having are not indicating any problems. And then, months or years later, they find out there was a, cancer going on, and it's too late to do anything because the doctor missed it the first time. They didn't run the test. They just accepted the results of the test rather than, trying again, even because the patient kept having symptoms, right? Inferential statistics, statistical tests that we would use are the Z test. If your sample size is 30 or more than 30, if your population standard deviation is already known, then you can go ahead and use a Z test. For instance, a company claims the average delivery time is 30 minutes. You collect 700 samples of someone ordering the pizza and they get the pizza within 30 minutes. Actually, 30 minutes is a long time for pizza. Let's pick something else that doesn't get cold and gloppy after only a half hour, right? So, but you collect a large sample to test a claim. If your sample size is small, you're not able to get a large sample, right? The t-test, and actually the t-test was developed for testing beer brewing back in the 1700s, no, 1800s, I'm sorry. And they didn't know what the true population standard deviation was. They didn't want to spend a whole bunch of time, retesting things. So they came up with this concept of using a small sample. So they sampled 1 sample, compares a sample mean to a known value. 2 sample compares the means of 2 independent groups. Then the paired t-test compares means from the same group at 2 different times. Does the student's average score differ from 75? Are the scores of males and females on this exam different? 2 independent groups. Are we seeing that blood pressure is going down after someone starts a medication? Chi-squared test is used for testing the association between categorical variables, checking if gender is related to product preference. A/B testing here. Analysis of variance takes 3 or more groups to see if at least one is significantly different than the others. So we've got 3 sections of a class, for instance. Is there a significantly different average score in the 3 amongst the 3 classes? Your confidence intervals. Your confidence intervals estimates how confident you are within the result. So if I have a 95% confidence interval, that means I've got 2.5% on either end for a total of 5%. That's my error space out there. I've gone, if I get that statistic, I reject the null hypothesis. I would have made a mistake. So I'm 95% sure that I haven't made a mistake. This is listed in here as 1.96 standard deviations away from the mean. Formula for confidence interval. Confidence interval is the sample mean plus or minus the confidence level value multiplied by the standard deviation divided by the square root of the sample size. Sample mean is 50, standard deviation is 10. Go ahead and run that calculation. We get our confidence interval of 46.08 to 53.92. That is, if we see a value outside that range, we start saying maybe I should reject the null hypothesis. 95% confidence interval means we're 95% confident the true population mean is within that interval. So if we get an interval of 46.08, We are, 95% of the time we do a measurement, 95% of those observations will be within that range. Okay. That is the end of our probability thing. And I don't think I have time to go on to another topic, so we're going to call it quits there and go ahead and do the attendance recording. So see what you think of